Swayamprabha. Digital India. Educated India.
Welcome you all to the course of Microfluidics. Today we will be starting with some introductory concepts related to microfluidics, and before entering into the topic we will be discussing about certain motivations which give us the necessary impetus to study microfluidics. So, but first of all we have to understand what is microfluidics and why is it important and what are its possible applications, and we will go forward with that. Now, microfluidics is not a technical term as such, it is not a scientific term, it is sort of an interface between various subjects, and its interpretation depends on the manner in which you look into it. Like for example, like microfluidics, it may have the name micro, but in terms of its scope it is like an elephant. It has a gigantic scope by itself. Now, if you want to say, somebody wants to say what an elephant is, now somebody who knows the tail of an elephant will say that the elephant is like a thread. So, obviously it depends on how you look into it. So, microfluidics being a multifaceted subject, its interpretation depends on how we look into it. Now, although this is an interdisciplinary course, this course is being offered as a part of our mechanical engineering curriculum. So, we look into it from a particular perspective and accordingly describe microfluidics like this, that microfluidics is all about studying flows with characteristic length scales of the orders of microns. So, what is a characteristic length scale? Characteristic length scale is a length scale over which characteristic changes take place. So, when we say that the characteristic length scales are of the order of microns, what we essentially mean is that the characteristic changes that take place, these changes take place over length scales of the orders of microns. Now, when we say microns, there is no great sanctity about it, it could also be nanometers. Now, there is a closely related subject which is called as nanofluidics, a part of which we will also cover as a part of this particular course, and when we go down to the length scale of nanometers, it is not necessary that all the physics which is occurring over micrometer scales becomes invalid, right. Over nanometer scales also, typically beyond the critical length scale, the physics which is occurring at the over micrometer scales is still valid, but as you go down to length scales over which continuum considerations do not work, continuum hypothesis does not work, and you have to treat the discreteness of the individual system. That means you have to consider the discreteness of the molecular arrangement, you have to consider the molecular entities and all those things. Then the paradigm shifts a little bit, and many of the continuum considerations which we will be considering as a major part of this particular course will not be valid, and then you have to go for molecular understanding and molecular simulation. So, a part of this course we will dedicate towards that. So, understanding nanofluidics and how to effectively address nanofluidics through molecular simulations, but we have to understand that nanofluidics does not necessarily demand molecular simulations. It is not always necessary. Sometimes by stretching a little bit of imagination towards modifying the continuum description, one can address many nanofluidics problems. So, whatever I am giving as like the description of microfluidics is a way in which as a fluid dynamist I look into microfluidics. So, obviously, I will show you that microfluidics is an interdisciplinary subject, and it is not possible for an individual to know all the facets of microfluidics from all the angles and from all fundamental considerations, but we will briefly talk about all the facets. So, when we say characteristic dimensions of the orders of microns, I mean as engineers we should have a feel of how thick or how thin these are. So, typical dimensions of the orders of microns are like dimensions of human hair, like so that is the typical thing that you talk about. So, if you have a transparent substrate on which you have a micro channel, it will look like a scratch if you look by a naked eye. So, microfluidics devices, and their dimensions. So, if you look at this view graph, you will see that there are wide ranges of dimensions of microfluidic devices. So, as I said that there may not be sort of hard and fast distinction between microfluidics and nanofluidics, and you can think of nanofluidic devices even of the order of angstroms. It is not that engineering has made it possible to make those devices very effectively, but we have to understand that the whole advent of the subject microfluidics had come into the picture because of the advancement in micro and nano manufacturing or micro and nano fabrication processes, because many of the underlying scientific issues have been studied and have been reasonably well understood for a long time, but engineers could not translate those understandings in the forms of devices until and unless there has been a significant advancement in fabrication, micro fabrication and nano fabrication. So, keeping that in spirit, fabrication over small scales will also be a part of this course. So, we will sort of try to see how fabrication influences fluidics and how fluidics influences fabrication. These considerations we will come across. Now, so we can start with dimensions of the orders of angstroms to nanometers and micrometers, and then we can have sort of large length scales where the microscale physics may not be that important, but we have a sort of an intermediate length scale where some effects of microscale are apparent, although not very significant. Like for example, in engineering typically we talk about micro channels, nano channels. There is a terminology called as mini channel. Mini channel is sort of like it is not micrometer dimension, but it is not also macroscopic channel. So, it has its characteristic features somewhat in between the microscopic and the macroscopic channel. So, these are all terminologies. I am just trying to make you familiar with the terminologies, but keep in mind that these are not scientific terminologies. These are terminologies which have been coined by people to describe certain technologies. So, like if you are thinking of like how these dimensions relate to real applications, like when you talk of angstroms to nanometers, you think of molecular dimensions, right, of the orders of angstroms, and then nanometers to micrometers you have smoke particles, viruses, and over this regime you have nano devices, and the common buzzword nanotechnology is used for technological applications over these length scales of nanometers to microns. So, little bit of larger length scales, you think of like other substances which closely relate to microfluidic devices, like for example bacteria, and you can think of substances or devices which are closely associated over these length scales, like microneedles, micro reactors, microfilters, microanalysis systems. So, these are many terminologies which are used for microfluidic devices. Now, microfluidic devices are commonly associated with certain names. For example, many microfluidic systems are integrated in the form of a chip. So, it is like a credit card type of device on which you can have all operations of a laboratory like mixing, metering, valving, pumping, all these fluidic operations which you normally do in a processing industry, it may be chemical processing, biological processing, all these are miniaturized in the form of a small chip, and these types of devices are called as lab on a chip or laboratory on a chip. So, the lab on a chip, and many of these lab on a chip devices are used for certain chemical analysis or biotechnological or biomedical analysis, and then these have alternative names as micro total analysis systems. And I mean these names are so popular that, right, for example, there is a journal called as lab on a chip, or you have like a conference named MicroTAS. So, there are I mean these names have become quite popular to the community. So, and just to give you an idea of the volume flow rates that these devices can handle. So, like typically they will be in the range of femtoliter to picoliter to nanoliter to microliter, and not very commonly beyond microliter, because beyond microliter you enter into millimeter dimensions of laying scales. So, typically whenever we are talking about microfluidic devices, we are essentially talking of devices which can handle small volume flow rates or which are designed to handle small volume flow rates. Now, when we say microfluidics, of course, all of you have a fair idea that these days micro and nanotechnology, these are very fascinating areas of research. I mean these are very popular areas of research, not just in any specific country, but globally. The question is that why we should go for microfluidic devices. I mean what are the advantages that these devices are going to give us? Is it totally because of fashion, or there are scientific or technological interests in the background? So, here are some reasons why we go for miniaturization. So, this is not true just for microfluidics, but for any devices where we are intended to miniaturize the product. So, the first point is one can minimize materials and sample consumption. So, why you can minimize the material consumption is because the device itself is small. Now, sample consumption, I will give you an example. Let us say that you want to perform a blood test. So, medical diagnostics is one of the applications where which we will discuss briefly now and much more elaborately as we proceed in the course. Now, if you want to test a blood sample, if you have one drop of blood, then the amount of chemical reagents that are necessary to test the sample will also be of small amount. On the other hand, if you have a large amount of blood as a sample, then you require large volume of chemicals. So, we can see that in a miniaturized system you may require a small volume of the reagents to achieve the necessary task. Not only that, because of miniaturization one can run the device with low power. So, one can reduce the power budget. Many of these devices operate fast or operate because of favorable scaling over micro and nano scales. So, we will discuss about this, the different forces scale favorably as you reduce your dimensions. For example, if you reduce your dimensions, you will see that surface forces become more important. So, surface forces can help the transmission of fluid, which are otherwise active, but not so important over large scale systems. So, one can use that favorable scaling, increase selectivity and sensitivity with nonlinear effects, exploitation of favorable scaling laws which I have already explained, and exploitation of new effects. So, some effects which are not, when I say new, what I mean is that which are not very intuitive, over large scales, some of those effects may become important. So, keeping that in purview, we say that miniaturization is not always a fashion, many times it is essential. Not only that, miniaturization achieves certain thing which is very practical, it makes the device small, it makes the device portable. See, you think of the old day computers, gigantic, and you think of the modern day computing gadgets, I mean which have become slimmer and thinner. So, you can carry them and you can work while you are traveling. So, I mean it is not always just the scientific need, but the demand from our fast changing lifestyle that has also given rise to the advent of miniaturization based technology. Question is, what are its applications, or why is it important? We will go for applications, but first why is it important? Microfluidics is required when the application demands handling of very small volumes. As we saw in the previous slide, that the volume flow rates that are handled in a microfluidic device, these volume flow rates are small. Because the volume flow rates are small, you cannot use these devices for applications where large volumes are required. So, you essentially use microfluidics for those applications which require the use of small volumes, like inkjet printing. In fact, inkjet printing or inkjet printers are sort of the first generation microfluidic products used in the industry. It was in early 1980s that inkjet printers were introduced in the market, and in those days the subject was not known as microfluidics. I mean it evolved as a subject by itself, but I mean that was one of the technological revolutions so far as microfluidics is concerned. You can use small volumes for precise drug delivery. For example, if you want to administer very small volume flow rate of drug very precisely to certain diseased cells, then you can use microfluidics. Cost or performance advantages. In many cases, we want to use microfluidic devices because they are less expensive and they have some advantages of performance by exploiting the science. So, microfluidics is sort of a is located at a nice interface between science and technology. So, on one hand, the objective of studying microfluidics from an engineering point of view is to make new devices for certain applications, but these new devices have to be designed based on some fundamental scientific principles which come from the basic principles of physics, chemistry and so on. So, it is at a nice interface. Improved reproducibility, accuracy and reliability is what we expect that we have in microfluidic devices, although there are questions I mean or issues to be addressed if we want to ensure this. Now, there are certain terminologies called as self assembly and self repair and which are closely linked with many of the microfluidic systems, although those are more associated with the nanotechnology than with a little bit larger scale systems. And many of the microfluidic devices, like for example, if you think of a microfluidic device for blood extraction. So, many of the microfluidic devices, they are not just functioning nicely because of the small scale effects, but they may also have minimal invasive pain. So, these are some of the features that we look for in microfluidic devices. Now, see, I am teaching this microfluidics course to you, but I must confess that I am not a big expert in microfluidics, because microfluidics is interdisciplinary. So, it requires the agglomeration of so many disciplines that it is impossible for one individual to be an expert in the entire gamut of microfluidics. So, for example, let me talk about what are the sort of specializations that are needed to address a microfluidics problem, and once you understand this, you will appreciate that any study of microfluidics is basically a team effort, and how does it go on. So, microfabrication, like to study microfluidics you require to fabricate microchannels, or if you go down to even smaller scales, fabricate nanochannels. So, these are jobs of fabrication or manufacturing specialists. Chemistry, over small scales surface chemistry can dictate the flow in a very interesting way. We will later on address those issues and see that how does surface chemistry alter fluid dynamics. So, but for the time being just take as it is that chemistry of the surface can dictate the flow in a very interesting way. So, one requires chemistry. Biology, it is not that one has to be a core biologist to work with the interface between biology and microfluidics, but most of the or many of the challenging applications in microfluidics are actually from the area of biology. So, that is why many times like I have seen this experience, I have gathered this experience that I mean when somebody some person, some professional working in microfluidics is asked that well what is your like specific area of application in microfluidics. He says I worked in two areas, one is bio applications, another is non-bio applications. That means it shows that bio applications is sort of a big thrust area of activity by itself. So, it is so important that a big application area of microfluidics has emerged, which we call as biomicrofluidics, and that also we will cover as a part of this particular course. So, and again the importance of the subject is such that there is a journal called Biomicrofluidics. So, like biomicrofluidics is a very active area of research. Mechanics, like I mean there are hardly engineering systems which we can think of without thinking of basic mechanics, and microfluidics is of no exception. So, mechanics is important, and in particular we will talk about mechanics over micro and nano scales. So, sometimes the classical laws of mechanics a little bit sort of they have to be explained in the light of small scales, not that they become totally invalid, but they have to be explained in the context of small scales, and that is where mechanics becomes so attractive in small scales. Control systems. So, when we say control systems, what we essentially mean is that just like any engineering system, if you have a microfluidic system which executes certain tasks, I mean many of the microfluidic systems are electromechanical systems, and a closely related area which I mean which can be thought of as a more generic area is micro electromechanical systems or MEMS. So, sometimes we associate microfluidics very closely with MEMS, and in fact for many of the MEMS applications microfluidics appears to be a building block. So, in many of these systems you have to design a very nice control system for the system to operate efficiently, and control systems become critical. Microscale physics and thermal fluidic transport, I mean that is where we will mainly focus on in this particular course. So, by microscale physics what we mean is that like the classical mechanics of fluids that we study commonly, I mean many times I mean it is not that all those equations that you have learnt in your basic fluid mechanics will be invalid, but those equations sometimes do not take into consideration certain features which are not important at large scales, but as you scale down your system, those features are important and those features have to be taken care of. Numerical modeling.